let's suppose for a moment that I collect a bunch of data in the laboratory, and then I decide that the best choice of expressions that linearize the data is to choose to plot on the x-axis 1 over x, so 1 over x on my x-axis, and e to the y on my y-axis. So this is how I like to write that in notation, that in my transformed axes I'm plotting kind of capital X versus capital Y, where capital X and capital Y are expressions in little x and little y. And so the question that I asked, and this is what was done I think in question I2, the question was, this happened also in 4.23 in the book. So if when I plot 1 over x versus e to the y, and if that plot is linear, then what model equation does the original data, x and y, little x and little y, what model equation is satisfied in the original data? So group that worked on question I2, what did you do here?
What we did was I first just wrote down y equals mx plus b.
Okay, y equals mx plus b, where the y and x's are the capital Y and capital X here, because it's a linear equation on our transformed graph, so this graph over here. Okay.
Then from there I substituted in the big Y and the big X, or capital Y, capital X.
Right.
1 over x and e to the y.
Right, so e to the y now takes the place of our capital Y. 1 over x takes the place of our capital X. And so I get something that looks like this. Okay. Then what? What would you do?
A log, right?
Right. Because if we want to determine what model equation is satisfied by x and y, we want to rearrange this thing to make y the subject, make our dependent variable, our original dependent variable, the subject. And so, in this example, that would just be done by taking the natural log of both sides. That will give us y by itself on the left-hand side, and what do we have on the right-hand side?
Natural log of mx plus m over x plus b.
Right, the natural log of m over x plus b. So in other words, if we transform our data in the way that's shown up here, using plotting 1 over x versus e to the y, if we transform our data in that way and we get something which looks pretty much linear, and in this example, the data points that I've plotted up here, they look fairly linear, then that means that our original data, our little x and little y, the data that we measured in the lab or whatever, will satisfy an equation that looks like this one down here. Y equals the natural log of m over x plus b. And then to find out what are the values of m and b that satisfy, that give us our equation in the original data, we'll just take the slope and the intercept from our linearized equation over here. So here was our m, and here was our b, right? The slope is the coefficient of the independent variable, independent expression in the transformed graph. The intercept is the additive constant. And so then I'm just going to drop in those values for m and b, and that gives me a nonlinear equation. Y equals the natural log of, and in place of m, I'm going to have negative 468.33 over x, plus b, 221.63. And that equation, y equals the natural log of negative 468.33 over x plus 221 over 3, that now is an equation for this curve in our original data. So that's the power of linearization, is that it takes data which doesn't look in any way linear, and we can fit a nonlinear model to it just by choosing to linearize the data in a particular way. And whichever way we choose to linearize our data determines what shape our nonlinear model is going to take. And going back and forth is just a matter of rearranging the equation y equals mx plus b for your choices of transformed variables y and x, rearranging it to make our original little y the subject will show you what model equation you have. And then going the other way, taking a nonlinear model equation and trying to find variables that linearize it, we can do the same thing. Just try and get something that looks like y equals mx plus b, and that will tell you what your y and your x end up needing to be.